Hi, welcome to Old School Chemistry. Today we're going to do the ALEKS topic, naming the shape of molecules with one central atom and no octet rule exceptions. Here's what you need to know about this topic, and I'm so sorry, they don't say it anywhere in this. They want molecular geometry, not electron, okay? Not electron, it's molecular. It's what I tell my students, if we could see the atom, the shape, this is what we would see. Now, electron geometry, that determines the overall shape of the molecule, but if we could see and look at the molecule, you can't see lone pairs, and that's molecular geometry. So be so careful. You have your VSEPR table that has both the electron and the molecular geometries on them. You are going to use molecular geometry on this. Okay, so first step, we always draw our Lewis dot structure. We have, a hydrogen cyanide. So if it's a gas, hydrogen cyanide. If it's aqueous, hydrocyanic acid. Very exciting. Okay, our central atom is going to be the atom with the fewest valence electrons. That's carbon. Right away, I know hydrogen has one valence electron, so I'm going to go ahead and do a single bond to that hydrogen. Carbon has 4 valence electrons. We shared 1 electron. I have 3 more electrons to share. Well, this is perfect because nitrogen has 5 valence electrons. So I'll share 3 electrons with the nitrogen. The nitrogen shares 3 electrons, and that's going to leave a lone pair. So the hydrogen senses 2 electrons. Perfect. Carbon senses 2, 4, 6, 8. There's the octet. Nitrogen, let's go back to its 5 valence electrons. It shared 1, 2, 3. There's a 4, 5. But now, because it's sharing, it senses 2, 4, 6, 8. An octet. Beautiful. Okay, from this, we're going to count electron domains. In fact, let me write this down. Step 1, you're going to write the Lewis dot structure. Step 2, you count the electron domains. Now, a reminder on this. One electron domain, here's what qualifies as one electron domain. A lone pair, single bond, double bond, or triple bond. Remember, an electron domain is just an area where electrons exist. It doesn't matter how many electrons are in that area. It's just how many electrons exist. I like to tell my students, when all of my kids were at home, we had 7 people in our house, 5 beautiful girls. So our house, a domain, had 7 people. Our neighbors, however, they had 1 daughter, they had 3 people. They're both domains. They're both houses. One had 7 people, one had 3 people. Same principle. Take a look at this. Here I'm going to count the electron domains around the central atom. The carbon has 1, 2. Now you and I totally know, yes, a single bond has 2 electrons, and a triple bond has 6 electrons. That's fine. Those are still 1, 2 total domains. This would be like our neighbor that had 3 people in their house and us that had 7. That's one domain, 2 electron domains. Now when you have 2 electron domains, no lone pairs, the molecular geometry is linear. That is going to be linear. Let's type this out actually, and we'll do another one together, okay? So linear. Check that. Always love it when we get the green correct. Woohoo. And now let's see what we get. Okay, a phosphorus trichloride. So step 1, we are going to draw the Lewis dot structure. Phosphorus has 5 valence electrons. I'm so glad we got this one. 5 valence electrons. 1, 2, 3, 4, 5. Remember our electron dot, you go 1, 2, 3, 4, 1 electron on each side, and then you double up. So there's a 5. Now, chlorine, just as a reminder, has 7 valence electrons. I go 1, 2, 3, 4, 5, 6, 7. It needs 1 more electron for a full octet. Easy peasy. I see how this is going to come together. We'll share 1 electron with each of the chlorines from the phosphorus. So it shares 1 electron, chlorine shares 1 electron. Do it again. Chlorine shares an electron, phosphorus shares an electron. Chlorine shares an electron, phosphorus shares an electron. Fantastic. And then let's check it. So, oops, bumped that. The phosphorus senses 2, 4, 6, 8. Hooray! It is a full octet. And each of the chlorine senses 2, 4, 6, 8, a full octet. Okay, now let's count electron domains. We have 1, 2, 3, 4. Remember, I said a lone pair can also be an electron domain. We've got 4 electron domains, but I'm going to be super specific since we need the molecular geometry. We've got 1 lone pair electron and then 3 bonded electron domains. Okay, molecular geometry. Now, let me step back. The molecular geometry on this is going to be trigonal, pyramidal. I had to think for half a second. Trigonal, pyramidal. Some of you maybe said tetrahedral. Tetrahedral, are you ready for this? Is the electron geometry. Electron geometry is based on all of the electron domains, the 4 electron domains. It determines the shape. Remember, molecular geometry, if we could look and see the molecule's shape, is what we see, and you can't see lone pairs. You can't see lone pairs. So if you think of the tetrahedral shape, here would be my phosphorus. I would have a lone pair sitting up here. You and I can't see that. And then we'd have 1, 2, 3 chlorines. There's your tetrahedral shape. I can't see this lone pair up top. You only see, looks like a pyramid, trigonal pyramidal, this bottom part that would look like a pyramid. Be so careful. This is molecular geometry. Let's type it in just because I want you to see the pyramidal. I want you to see, hopefully I spelled that right. Yep, there we go. I wanted you to see that that is correct. So you're using molecular geometry, not the electron geometry on this topic. And I'm so sorry they don't say it. I wish that they did. Alex, if you're watching this, go add the term molecular geometry. Okay, thank you so much for being here. Have a wonderful day. Like and subscribe. I'll see you next time.